Hi, this is Dr. Maria Weber, and our next mini lecture is about power, in particular, electrical power and electrical energy. Electrical power represents the movement of charge through a voltage per unit time. The energy that is expended is the electric potential energy, and that is equal to our charge times our voltage, which we learned before spring break. So our power, remember that power is equal to an energy over time. So we learned that last semester. So power is equal to our potential energy divided by time. So that's equal to our charge times the potential difference, or the voltage divided by time. Now, remember that current is also Q over T, or delta Q over delta T. So this power is also equal to the current times the voltage. So using Ohm's law, we can rewrite this equation in a couple of different ways here. So we have the first one, still power is equal to current times voltage. Remember that voltage is equal to current times resistance. And so we can rearrange that in two different ways to say that power is equal to voltage squared over the resistance. It's also equal to current squared times the resistance. So to get this last one here, we replace V with IR. So then we would have I times R. So that's I squared times R. Now for this one here, if V is equal to IR, then I is equal to V over R. So we replace this current with a V over R. So we have V over R times V. So then that becomes V squared over R. Now, power has units of watts. Electrical power has the same unit as the power that we were talking about last semester, which was like mechanical power, units of watts. And the unit of energy used by electric companies to calculate energy consumption is the kilowatt hour, which we represent as K big W times H, kilowatt hour. So over here, we could solve this equation and say that energy is equal to power times time. And so an electrical company would calculate that energy that you've used in your home with the quantity or the unit of a kilowatt hour.
In this problem, we are going to immediately apply our idea of power and also think about Ohm's law. We're going to think about the power converted by an electric heater. An electric heater is operated by applying a potential difference of 50 volts to a nichrome wire, which we talked about nichrome wires already, of total resistance 8 ohms. Find the current carried by the wire. To find the current carried by this wire, well, we have Ohm's law. Ohm's law says that the potential is equal to the current times the resistance. In this problem, we're told the voltage, we're told the resistance, so we can solve Ohm's law, V is equal to IR, for the current. Then we find that if we do that, that the current is equal to the potential difference, or the voltage, divided by the resistance. So we'll take our 50 volt potential difference that's applied to our electric heater, divide it by the resistance of the wire. So then if we take 50 volts divided by 8 ohms, that gives us the current that's carried by the wire. That's the current supplied to our electric heater, and that is 6.25 amperes. And the unit of current is amperes, capital A here. Then we're going to find the power rating of the heater. So there's 3 ways you can find power, and which one you choose just depends on what you're provided with in the problem. We could actually use any one of these relationships for power. We just found the current and we were given the potential and the resistance in the original problem. So we can use any one of these relationships. Power is equal to I times V, it's equal to I squared times R, or it's equal to V squared over R in order to solve for the power. Any of these relationships would give us the same number. I just chose to use the middle one here. Power is equal to the current squared times the resistance. So our current from part A was 6.25 amperes. We square that and we multiply it by the resistance, 8 ohms, and that gives us our power of 313 watts. That's the power rating of the heater. So if you are asked for something or hear something about the power rating of an electrical device, the power rating is how much power it can dissipate, how much power it needs to use in order to perform its function. We're going to use this idea of power in order to figure out how much it costs to power some electrical devices. You will also find this to be particularly useful when you are working on your discussion for this week. A circuit is going to provide a maximum current of 20 amperes at an operating voltage of 120 volts. But first, we're going to find how many 75-watt bulbs we can operate with this voltage source. And if we are being charged for electricity at a rate of $0.12 or 12 cents per kilowatt hour, how much does it cost to operate these light bulbs for 8 hours? All right, so for part A of this problem, for part A, well, we had a current of 20 amperes and a voltage that's being supplied to all of our bulbs of 120 volts. How many, so I'm going to say N equals question mark, how many light bulbs that are each of 75 watts can operate with this voltage source? When you look on a light bulb and it says 75 watts on the side, that means that it requires that amount of power in order to, light up as it does. Now, in order to find out the number of bulbs we can operate with this voltage source, first we have to find the total power that is supplied from our current and our applied voltage. So the total power available to us is going to be the current times the potential. And so that will be 20 amperes times 120 volts. So the total power available to us is 2.4 times 10 to the 3 watts, or 2.4 kilowatts. That's the total power that can light these bulbs. To find the number of bulbs that we can light with this power, we have to take the total power available to us that we just found, divided by the power required for each bulb. Okay, and that will give us the number of bulbs. You can also think about this as the total power is equal to our number of bulbs times the power per bulb. So to find the total power to run a whole set of devices, let's say you want to find the total power to run all of the devices in a room, you just add up the power consumed by each individual entity. Okay, let's say your room has like 52 lamps and they all have a light bulb in them. To find the power you would need in order to light all of the bulbs in that room, you would have to add up the power consumed by each of those 52 bulbs in your room. And that's the same thing as taking the number of bulbs that you have and multiplying it by the power per bulb, assuming that all of those bulbs consume the same amount of power. So the number of bulbs we can supply with 2.4 times 10 to the 3 watts of total power is that total power divided by our 75 watts per bulb. And our units of watts cancel on top and bottom. And so we see that we could power 32 bulbs, each of 75 watts each, with our power available to us of 2.4 kilowatts. Now, so that's the answer to part A. For part B, we have a cost of 12 cents or $0.12 per kilowatt hour. At $0.12 per kilowatt hour, how much does it cost? Cost equals question mark to operate these bulbs for 8 hours? Question mark. Well, this is when we're going to use our relationship for power and energy. Remember from last semester, power is equal to energy over time. So our energy is equal to power times time. We want to find this energy consumed by our light bulbs because electrical companies calculate your energy consumption in units of kilowatt hours. So we need to find the energy that all of these bulbs are consuming by taking the total power of all those bulbs acting together times the amount of time that I'm keeping those bulbs on. So the energy will equal the power needed to run my 32 bulbs, which was 2.4 times 10 to the 3 watts. And I want to multiply that by the time I'm keeping them on, which is 8 hours. Okay, so if I do this calculation, I'm going to get my answer in watts times hours. But our unit for cost here is given in money per kilowatt hour. So actually, I want to find my energy consumption in kilowatt hours. So 2.4 times 10 to the 3 watts. That's the same thing as 2.4 kilowatts. Okay, 10 to the 3 is 1,000. That's also a kilo. So 1 kilowatt is 10 to the 3 watts. 2.4 kilowatts times 8 hours gives me an energy consumption of 19.2 kilowatt hours. Now to find out how much it costs to run all of these light bulbs, my cost, I'm going to put it here, I'm kind of running out of room, is going to equal my energy consumed times my cost per kilowatt hour. This cost is then going to be, sorry, I'm running out of room here, my energy, which was my 19.2 kilowatt hours, energy consumed by my 32 bulbs, times the cost per kilowatt hour, which was $0.12 per kilowatt hour. And then that gives me a total cost to power to light up all of my 32 bulbs for 8 hours of $2.3 or $2.30. Okay, so if I ask you to calculate how much it's going to cost to power a bunch of electrical devices in some room in your house, you go around and you add up the power consumed by each of those items. That's the total power that those electrical devices will consume. Then, in order to figure out how much it's going to cost to run all of those for some time period, you use your equation here. Energy is equal to power times time. So I take the power that all of those devices consume times the amount of time I need to run them for. That will give me my energy consumption in units of kilowatt hours. And then I have to use some cost calculation for how much is the electrical company charging me. This particular electrical company was charging us 12 cents per kilowatt hour. So I take my energy consumed and I multiply it by the cost per kilowatt hour. And that tells me how much it's going to cost to light up all of those 32 bulbs for 8 hours. This is going to be your concept engagement question. And we're going to need to use our idea of power here in order to find this answer. We have a circuit set up here. We've got our battery supplying some potential and that creates a current in the circuit. That current is running through my circuit. Okay, so we've got the current coming through point A here, and it comes up through here and it has to split either through my resistor, this one here, or it has to split to go through the top resistor here. So these two resistors are in parallel. You've already learned a little bit about this for lab, right? Now the current has to split to go through either this top bulb or this bottom bulb here. Well, we can say that they're light bulbs. There's some kind of resistor, okay? Light bulbs are resistors in the circuit as well. They can be. This top resistor has a power rating of 30 watts. This bottom resistor has a power rating of 60 watts. With that information, you're going to rank the current at points A, B, and C here from least to greatest. Okay. Now remember, all of our relationships that we use for power, power can equal I times V, it can equal to I squared times R, it can also equal V squared over R. Okay, so let's see. So I'll give you one hint. In our total circuit here, the greatest amount of current is going to be right here at point A, okay? And then that current has to split to either go through resistor B or go through resistor C. So we know that the current through B and C is going to be less than the current through point A here, okay? Now, we remember, let's see, think about our equations for power. Let's use the equation power is equal to current times potential. Now, the potential is fixed, it's being supplied by our battery here. And since both of these resistors are in parallel, they both experience the same potential across them. We also learned that in lab already, right? So with that information, and we also know the power rating here, what's the current flowing through each one of these circuits? You're not going to be able to get an actual numerical value, but if you solve that equation for power is equal to I times V, solve that equation for I, you have a quantity for power here and V is fixed. So which one of these resistors has the smallest amount of current running through it? Is it going to be this top one that consumes 30 watts, or is it going to be this bottom one here that consumes 60 watts? And when you think about that, you're going to rank the current running through this point A, B, and C from least to greatest. And so the current has to flow through A, and then it has to split to go through B and then enter this resistor, and then or split to go through point C and enter this resistor. And the current that's going through point C is the same as the current going through this resistor. The current going through point B is the same as the current going through this resistor.